So let's get into this. We are going over sight, the sense of sight. And this utilizes the photoreceptors, or light receptors, receiving light from the outside world, processing it somehow so that your brain can understand it. Light receptors. Those light receptors are in the back of your eye, which means they need to go through your entire eye to get there, or the light needs to go through your entire eye to get there. So let's talk about the things in front of your receptors then. We have what we know as the color part of your eye. It's actually called the iris. And then the iris is surrounding your pupil. And notice, guys, the pupil is not shown black right here. It's because your pupil is not actually black. It's not actually anything. Right? The pupil is not even a structure. It is a hole. That's right. You have a hole in your eye, ladies and gentlemen. That way the light can actually enter. It only looks black because it's dark in there. But as the light goes through into the pupil, behind it is a lens we'll talk about that, like your glasses, bends the light. Or like a camera lens, puts things into focus. And then all that now focused light shines on the back of your eye where you keep your photoreceptors, which will then send information through your optic nerve into your brain. Yes, optic nerve. Just like your ears had the auditory nerve. Auditory means sound. Optic means sight. So these are optic nerves. Before we can actually talk about the eye, however, in detail, we need to talk about the things around your eye. We call these accessory organs. I mean, they're not technically part of the eye, but they are necessary to keep your eye functioning properly. So here are the accessory organs of the eye. Your first one is the lacrimal gland. Lacrimal gland.
Lacrimal.
It's a tear gland. This is where your tears come from. It is kept superior and lateral to the eye. Now, why am I going back and using those directional terminology terms again? Because you have two eyes. And the positioning of that gland is different on either side. So I can't say it's to the left because on your other eye, it's to the right. But they're both lateral, off to the side, and superior. So it's above too. And your tears are going to leak out of this gland and go medially across your eye toward the center. So yes, your tears don't go straight down your face. They actually go across your eye, cleaning your eye and keeping it moist. So you're actually crying right now. You probably don't even know it, but yeah, your tear gland is constantly going. You are constantly crying. It only runs down your face when you're overproducing. And instead of running down your face, there is an opening this side of your eye where it leaks into your nasal passage, which is why if you're crying a lot, your nose also runs too. And it's also the reason why when you wake up in the morning, sometimes you get those crusties in the corner of your eye, you gotta wipe them out because all the dust that's collecting throughout the night as you're laying there get washed to the side and the water leaks down here, but all the dust stays behind and builds up. Another accessory organ is your eyelid, which is going to help spread those tears, kind of like windshield wipers, right? Moving the water around. And it's also going to be protection. All the dust and spores and pollen and stuff in the air that you don't want entering your eye and like absorbing all that liquid, making your eyes dry. Your eyelids shut to protect you. And also protects you from excess light. Too much light can hurt. And those other accessory organs were not technically part of your eye. These ones are a part of your eye. They have nothing to do with helping you see things. These are muscles that are going to cause your eyes to move. Remember, anything in your body that moves requires a muscle to do so. Each of your eyes requires 6 different muscles. That's right, 6 muscles each. I hear you asking, Mister, how do we have 6 muscles if there's only 4 directions?
Why are there 6 pedals if there are only 4 directions?
Up, down, left, and right. Well, you also got a rotational direction, right? You can move in like your eyes in a rounded motion. So the first 4 are your standard directions. We have the superior rectus right up here. Superior means above, and rectus refers to muscles. This is the above muscle of your eye. And when you pull, when it contracts, it's going to lift your pupil up, make you look upward and slightly inward. By the way, picture the nose being right here. Right? You have an eyeball and the nose and another eyeball just off screen. Right? So this is the right eye. And so it's going to make you look up and kind of inward. Then you got the lateral rectus. Lateral means to the side, away from the nose, right? Off. So when this contracts, your pupil goes this way. And then you got the medial rectus. When this contracts, it's going to bring your pupil in toward your nose. And then the inferior rectus. When this contracts, it's going to pull your pupil down, make you look downward. Those are your 4 normal directions, but then we got these 2 weird ones, here and here. Those are the superior oblique and the inferior oblique. So this is kind of side muscles above and below. And they're not technically here. It's kind of drawn closer to the front so you can see it in this picture. I have a model, if I can find that model. Here we go. So I don't know if you guys can see here. Here is my model eyeball, superior rectus, and then behind it, we can see the superior oblique is actually coming, I'm going this way maybe, attaching to the back, not the front like it is in your notes picture. So we are in the back of the eyeball. This superior oblique is more to the back. So when this pulls up, it's going to bring the back of your eye up, which means the front of your eye is going to go down. And it's off on the side, so it's going to make your eye go down and out. It's a rotational motion. And then your inferior oblique is the exact same thing, but from the bottom. So it's going to make you go up and outward. Again, another rotational. All right, the first part we're going to go over is the white of your eye. It is known as the sclera. The sclera, the white of your eye, is made out of the same stuff as your tendons and ligaments. Very tough stuff. It is there for protection. The cornea, would you look here, is a clear covering. It's actually technically part of the sclera. It's the same material, the same fibers that make up your tendons and ligaments, that same connective tissue, except that the alignment of the fibers change in the front. It's really weird. Like, they line up in just the right way that you can see right through them. Light can pass through. And it is going to, again, protect your eye. And it does have a little extra job of helping focus light. Behind your cornea is a water balloon. Yeah, no, legit water balloon. That's its job, to be a water balloon. It's called the aqueous humor. Aqueous means water, and humor is just a fancy sciencey word for a sack of liquid. So it is a watery sack of liquid. And its main job is just to maintain the shape. Now, there is a bulging shape here, and that aqueous humor keeps it there with water pressure. Because God forbid this got loose and wrinkly, and then you would just have wrinkles in your vision for the rest of your life. So that is just shape maintenance. Behind that is the pupil and the iris, and these 2 things work together. In fact, the pupil itself doesn't do anything, because the pupil itself isn't anything. It's a non-structure. It's just a hole. People think that the pupil is this black dot in your eye, and it's not. It only looks black because it's dark inside your eye. There's no light in there. It is just an opening. The iris is the actual doorway. It is a colored muscle. Its whole main function, though, the actual muscle part of this iris, not the color, but the muscle, is to change the size of this hole, this pupil. As the muscle contracts this way, this pupil will get bigger. So if you're in a dark room, the muscle will contract, pupil gets bigger, and more light can go in your eye. If you are in a bright room, the muscle relaxes, making the pupil smaller, and less light goes in. Behind that iris is a lens. Yes, a legitimate lens, like the lens of your glasses or the lens of a camera. Its job is to bend light, to refract light, put things in focus. So as the light goes in, just like the camera lens, it will get the focus will get changed so you can see it better in the back of your eye, which is where vision is actually happening. So if someone is really far away and they're blurry, there are muscles. You see the muscles right here? These muscles are going to pull on this lens to change its shape, because that's how your glasses work, right? Different bends in the glass make different prescriptions. So we're using muscles to bend the lens to change the prescription, and that person who's really far away, who's blurry, comes into focus. And when they run up close to you and they're blurry again, the muscles change the shape of the lens again, and that person comes in focus. And beyond that is something called the vitreous humor. Kind of like the aqueous humor in the front, except vitreous means like jelly-like instead of watery. So it's a water sac in the front and more of a jelly sac in the back. And it's going to have the exact same job as the aqueous humor, maintain shape, because we need all of your photoreceptors in the back to stay put. We don't want them moving. We don't want this to become like a deflated balloon and your photoreceptors to shift around. So this vitreous humor is going to be like a water balloon pushing against the sides, keeping your eye round and your photoreceptors in the right spot. All those photoreceptors are held in place not just by the vitreous humor, but also the retina. Your retina is like wallpaper. That's what's plastered against the sclera. There's the vitreous humor is holding the retina against the wall, and your photoreceptors are intertwined in the retina. So if the wallpaper falls, the receptors go with it. And that attaches in the back to the optic nerve. So here's how your eye is going to work with all those things together. This is Carl. Say hi, Carl. Say hi to Carl, guys. He's a good guy. I like Carl. All right. Now, Carl is standing out in the sun or under a lamp or in front of some candles, whatever. There's a light source, and that light is reflecting off of him. And the light bounces off of him and into your pupil. But then we got the lens. You guys ever look at your reflection in a spoon? Like the inside bend of a spoon? Did you ever notice that you're upside down? Same idea here, guys. So the top of Carl's head hits here and then bends downward. His elbow hits here at the bottom, but bends upward. So you are actually seeing Carl upside down. You're seeing everything upside down. But remember what I told you about your brain and projection. This is a sensation, but then your brain tells you what you see, and that's a projection. Your brain is going to flip the picture upside down. Technically, you are seeing the world upside down, and technically, you're seeing the world twice because you have two eyes. Your brain is flipping the picture right side up and putting the two pictures together, overlapping it, and that's how you judge distance. And your brain builds one three-dimensional picture instead of two two-dimensional pictures. In that retina, those photoreceptors, we got 4 different kinds of photoreceptors. The first kind are called rods, and the other 3 kinds are called cones. The rods only handle black and white. That's it. The brighter the light is, they pick up brightness. The brighter the light is, the whiter it looks to you. The dimmer the light is, the darker it looks. If you're only using rods, then you would see the world in black and white. Cones, on the other hand, make up the other 3 kind. Those are your colors. The cones are going to detect color, and you only get 3 colors. That's it. You can only see 3 colors: red, blue, and yellow. That's it. Your entire world, the entire rainbow of your existence is actually 3 colors. But remember, your brain tells you what you see. You're not seeing what you're really seeing. You are believing what your brain tells you you see. So you look at me right now, what color shirt am I wearing? Green? Are you sure? Because your options were blue, red, and yellow. What you're really seeing, guys, is blue wavelengths bouncing off my shirt and yellow wavelengths bouncing off my shirt. And they blend together, and your brain processes both of them and tells you to color green. So your brain tells you green even though it's blue and yellow bouncing off my shirt, or blue and yellow bouncing off of my celery. Although technically, the other colors do exist. The entire rainbow of color wavelengths do exist, but your eyes only know how to detect 3 of them. And your brain has to compensate. So, what would happen, ladies and gentlemen, if you were missing one of those cones? Let's say red. Your red cones did not work. Just a mutation you were born with. Here's what it would look like. And this is what scientists think how dogs see the world, by the way. They say dogs are colorblind. Partially correct. They're not black and white colorblind. Dogs are unable to see red because they don't have red cones. We know this from eyeball dissections. So all the red disappears, and there is red tones to your skin, and they disappear, so you look kind of yellowish. So this is how your dog probably sees you. That is it for class right now. You guys have a great day.